How can we compute integrated information? So integrated information can be computed in relatively simple systems. Okay? And I'm going to talk about the introduction of the integrated information using these simple systems, because understanding how it's computed is going to give us some ideas about the essence of IIT, and especially how to estimate the integrated information in a real brain, and how it also differs from the approximation like PCI and so on. And the key ideas here are what it means to have various information that is relevant for consciousness, and also integration. And to explain these concepts, I'm going to use IIT in 2.0 version. And I kind of outlined this explanation of IIT in 2.0 in 2007 paper, and that is relatively easily explained in the for the philosopher audience. So overall idea behind integrated information is the following. First, you want to determine all possible states for a given system, like a network or subsystem or system can be in. And in this sense, I already mentioned about sort of the thought experiments of the photodiode or neurons last week. And photodiode can take state of on or off, neuron can take firing or not. And if it's only one, then there's only two types of the states. But if you combine many different kind of photodiodes or neurons, the number of the possible states itself can become big. But depending on whether it's integrated or not, that changes the degree of integrated information. And the camera example versus brain example talk about the integration. And then, but before going into the integration part, we first need to determine how much of its future or past states are constrained or determined by its current state. And this is called intrinsic information. And here, the important thing to understand is that it is to characterize the way it is rather than what it's going to be like in terms of prediction or sort of quantification. So the information in IIT sense is really about the way it is. Same for our conscious experience, whether we can talk about that, whether we can differentiate some specific small things or not is not really relevant, but the way we are experiencing the world, that is more important. And then we evaluate how much the system changes when it's minimally cut. And then this operation gives us the estimate of the integrated information. And again, the important thing is that the way the system is can change when the system is minimally cut. And that's the part that we are interested in for conscious experience, relevant information and integrated information. Okay. So, but the first thing first. First, we are going to talk about what we mean by all possible states and so on. The simplest system I'm going to talk about is this two neuron system, neuron A and neuron B. And each of the neurons can take either on or off state. And then by this gray circle, I will talk about, each can be taken, both can be, possible. And then as a rule of the causal interaction between A and B, I'll talk about the copy. So what it means is that if the neuron A is on at time one particular time point, then at the next time step, neuron B becomes on. And then if the neuron B is off, then neuron A becomes off. And that's the sort of the implied by this arrow of copy interaction. Okay. And then now let's think about the particular situation where currently this particular system is that the neuron A is on and neuron B is off. On is white and then off is black. Okay. And then, but there can be 4 possible states that this two neuron system can take, right? Both on, white, or off, black, or on, off, or off, on. So there are 4 possible states of this system. Okay. And then if the current situation is that both on and on, then the next step has to be off, off, and so on. But then let's think about the current state is off, on, and off. Then the next step is completely determined, off and on. And then same goes for the past. If currently it is on and off, then the last past step has to be off and on. It's completely determined. And this leads to us to this quantification of the intrinsic information of the AV. Now, what it means is that determining all possible states is 4 states, and then determining how much of its past or future states are constrained or determined by its current state is that completely determined, right? Out of 4 states, we have only 1 state left to take for the future or past. And that's using information theoretical kind of notion, or log base 2 is computed as a 2 bits, log 2 of 4, if you know about this logarithm. And so that's also the amount of the information that current has. Now, what happens if we cut or replace with noisy connections between this and A and B? I'm going to talk about the cut in the next few slides or few sections. But what I mean is always to replace that connection with the noise, where you can't predict anything that can happen in the future. Okay, so then let's say between A and B, now so far we had this very reliable copy kind of directional connections. But now we are going to replace that with a noise. Okay, then even though A wants to transmit it into off, then B itself can receive anything on or off. And what happens is that even if current state is on off, then because of this intervening noise, the A itself can become on or off 50-50, and B also 50-50. And the same goes for the past. Either on or off can result in the current state of on or off. Like even if neuron A itself was on or off, currently the B can be off. There is no prediction, no explanation about the future or past. That's the way this system is. Okay, and then as a result, this quantification of how much the system changes can be formulated like this. So when it is minimally cut, that's the important thing. The integrated information can be computed as original amount of the constraint that system has on its own minus information after the minimal cut. And in this case, it is 2 minus 0. 0 after the minimal cut, because after the cut or after the replacing its noise, we don't have any way to constrain its future or past. So 4 possibilities are all equally possible. And that corresponds to the 0 bit. And the 2 minus 0 corresponds to 2 bits. Therefore, this system has 2 bits of integrated information according to IIT 2.0. So now, just to summarize, integrated information from axioms to postulate in terms of information, and this is a figure for the information postulate. Consciousness information of axiom set. Consciousness is specific. Each experience is the particular way it is, being composed of a specific set of specific phenomenal distinctions, thereby differing from other possible experiences or differentiation. And this corresponds to, or IIT proposed that to support intrinsically informative conscious experience, there must be physical system that is intrinsically informative. And the way sort of the proposed to quantify that is to evaluate how much a system constrains the way it is in the past and future, given the current state. So in summary, in this section, we computed integrated information according to IIT 2.0 formulation for a 2-neuron system. Okay, and the 3 steps that we took are: first determine all possible states for subsystem. And in this case, in the 2-neuron case, it was four states. And then determine how much of its future or past state are constrained by its current state. So, if on off, then the future has to be off on, and the past has to be off on. So it's completely determined, and that's a lot of intrinsic information. And then evaluate how much the system changes when it's minimally cut. And in this case, because there is only one way to cut, A and B is cut. And then if it's replaced by the noise, A can become on or off, B can become on or off, or it could come from on or off in the past and so on. So there is nothing to constrain the system. That means that there is no intrinsic information after the cut. And therefore, the subtraction gives you 2 bits of integrated information, okay? So then I've been quite liberal about what it means to have this minimal cut. Now, what is the importance of the minimal cut is the one that I'm going to talk about next.